Hello and welcome back to the discussion sessions of production technology, theory and practice. So, let me remind you that in our last session what we discussed are the practical machining operations, that means the processes, how they are performed. I have shown it to you in transparency in the slides, schematically how these processes are performed and how those tools look like. For example, in case of drilling, okay. So, the drill has been shown, what are the geometries and all, and then after that we have discussed the reaming, then tapping, okay, and it was told that after the drilling operation, the drilled hole has to be made, the quality of the drill hole has to be made in a better way. Okay. So, in that case we have to ream so that the already drilled hole surface finish can be enhanced, and then if we have to make the internal thread, cut the internal thread, then we use the tapping. So, as it is shown here in this slide, if you see, now here is the reamer. This has been already told that this is the process is the reaming process, where there is already a drilled hole and the accuracy of the drill hole or the surface finish of the drill hole overall partially, that has to be enhanced. So, this is the process when the internal thread is being made, this is the tapping, and this is the counter boring. That means, when you have the two holes of two different diameters on the same axis. So, you can see that after this is made, there will be a part with two holes, one hole is here and one hole is here, and they have a common axis. Okay. So, this process is called the counter boring, and I told you that counter boring is made so that a special kind of bolt can be inserted here, so that the bolt head does not protrude out. Okay. It will be sunk. So, it is, that is why it is called the counter boring. All right. So, there are also other purposes for which the counter boring is used, and that we will see later, and also some of the uses we will see in the laboratory. Okay. Now, here schematically we have shown the milling process. This one is the peripheral milling. Peripheral milling, that means that the cutter axis is parallel to the surface that is being milled, okay, and the cutting edges on the outside periphery only. You can see that this is the milling cutter, this is how it rotates, and this is the axis of the milling cutter, okay, and this axis is parallel to the surface. This is horizontal, both in the horizontal plane, that is the surface that is being made and the cutter axis. Okay. Now, another process of milling process is the face milling. In the face milling, the difference between the peripheral milling and the face milling is that here first of all the cutter axis is perpendicular to the surface that is being milled, okay, and cutting edges, they are at the face, that means which is not visible. Face is at the 90-degree angle with the axis, okay, and on the sides, okay, and the outside periphery. So, this is the outside periphery, and here also we have the cutting edges in comparison to, for example, peripheral milling. In case of peripheral milling, it is on the outside periphery, here are the cutting edges, but here the cutting edges will be here as well as on the outside periphery. Okay. Here. Now, various milling operations, they are categorized as the slab milling. So, this process is the slab milling process, where the basic form of peripheral milling, in which the cutter width extends beyond the workpiece on both sides, if you see this, okay, meaning that in the case of the slab milling, in one go the entire width of the workpiece can be machined. So, this is slab milling. Actually, if you see the peripheral milling, okay, slab milling is one type of the peripheral milling. I will show you once again. If you see here, this is the peripheral milling, but this is the of course pictorial view, and here if you see in the two dimensional picture, the milling cutter is the same, okay, and therefore, the slab milling is one of the types of the peripheral milling. This is also a peripheral milling overall, because peripheral milling is a family of milling operations. Okay. All right. Now, the second process, this process schematically shown, this is the slotting. That means, here a slot is made along the length of the workpiece. So, this can be milling cutter is rotated, okay. In here we have the straight milling cutter, okay, and width of cutter is less than the workpiece width, okay. Width of the cutter is this, okay, creating a slot in the work, and this can be of a very long workpiece, and along the length of the workpiece the slot can be made, okay. So, therefore, you understand that it will rotate, and then the shaft along with the or arbor along with the milling cutter will be given a feed along the length of the workpiece. Okay. So, this is the slotting operation, and another operation of the milling is the end milling. So, this is the end milling here. End milling, the cutter diameter is less than the work width. Okay. Here there is a cutter diameter because it is the cylindrical. So, this diameter is less than the work width. So, a slot is cut into the part like in here. So, here the milling cutter is different than the one used here. So, this is the end milling cutter, this is called the end milling cutter, okay. And that these end milling cutters are very popularly used in practice for making grooves or making the contours, for example, okay. And similarly, in this slotting operation can also be made by the milling cutter, but the milling cutter is different. Here of course, it is the horizontal milling and this is the vertical milling. Okay. Here is the popular categorization of the milling. This is called the up milling. So, you must be familiar with that. This is the milling cutter and this is the workpiece. Okay. So, up milling is when the direction of the milling cutter, rotation of the milling cutter and the feed movement given to the workpiece are different. Okay. So, this is a common method of milling actually. Mostly you will see in practice the up milling is used. Now, the chip thin in the beginning, you can see from here when this one of the teeth of the milling cutter grabs the workpiece material, the chip thickness is 0, okay, and the chip thickness becomes maximum as it actually as the tool is given feed. So, if you see, I have already shown it to you somewhere earlier also, that this is a kind of a chip that can be produced. Okay. So, this is the chip, like here what we are saying is that when the tooth will be grabbed, tooth will grab the workpiece. So, the T1 is equal to 0 and here the T1 can be maximum. All right. So, this we have shown in the case of milling process, and we are again going to come to this in case of grinding, because as you understand that the in grinding process also the T1 becomes from 0 to maximum like in case of the milling. Okay. All right. Now, here what is said is that the workpiece has a tendency to be pulled up. Okay. So, as you understand that since these two directions of rotation of the work of the milling cutter and the feed movement are different, in that case when the milling cutter rotates, it will try to pull up the workpiece. Okay. So, therefore, the clamping forces should be more. So, to secure the workpiece not to get pulled up. Okay. And the tool engagement is not affected by surface characteristics or the surface scales. Okay. Scales means that when we have the hard particles, like for example, after the metal forming process. Okay. So, you will see that there are there is a black layer, and that black layer is strain hardened and is a very hard material. So, therefore, that particular layer of material we always remove before the operation starts, before the machining process starts. So, that is what it is said, that it does not depend whether the tool will be engaged properly or not by with the surface scales or the surface characteristics. Chips can be carried into the newly machined surface. This is another fear, that when the chip is formed here, these are the voids. Okay. In these voids, the chips are accommodated. So, when it is further rotated, this may rotate along with the chips located in the voids, that is the space between the teeth, okay, and it may actually fall on the already machined surface, this already machined surface, okay, because feed is given in this direction and the tool is moving in the clockwise, anti-clockwise direction. Now, therefore, the up milling, although it is used in practice because of some reason that I will tell you in the down milling, but then some of the disadvantages are also there. That means, it has a tendency to getting pulled up, okay, and of course, if the care is not taken, then the chips can fall on this and it can actually spoil the surface. All right. Now, down milling, the cutting starts from here. Okay. First of all, in down milling, we should tell that you can see here that the rotation of the milling cutter is in the same direction as the feed given to the workpiece. So, this is the down milling. Down milling is also called the climb cut. Okay. Now, the cutting starts at the surface where the chip is at its thickest. That means, it starts from the maximum chip thickness, it grabs and then it goes to the minimum. So, it is just other way around. All right. Now, here what happens, that since it grabs at a time at once, so the impact loading is very high. If you remember, we talked about this in case of the orthogonal cutting and the oblique cutting, and I told you that in case of orthogonal cutting, the tool grabs the material in one go at a time. All right. But in case of the oblique cutting, it grabs the material gradually. Okay. So, similarly, when in case of the down milling, when it grabs the tool with the maximum T1 uncut thickness, the impact loading is very high. All right. So, high impact forces require rigid setup. So, that needs a very rigid setup in the tool in the post, that is where the table machine milling machine table where the workpiece is clamped. Now, cutting force tends to push the workpiece down, reducing the clamping requirement. Okay. So, here you can see that this is the other way around, that this will try to pull down, push down. All right. So, when it is pushing down, that means your clamping requirement will be less, that means clamping force that is required, as in case of the up milling, for example, where there is a tendency for tool to pull up the workpiece. So, in this case therefore, the clamping forces will be less, but here there is one fear, that since it is in pulling, okay, and pushing down. So, there is a tendency for this workpiece to go towards the place where the operator is standing. So, one has to be very careful that if the clamping is not suitable, clamping is not proper, in that case the tool may actually throw this workpiece towards the operator where the operator is standing. Now, chatter will be less, because here this is because the T1 starts from the maximum, that is one point. Not suitable for workpiece with hard abrasive scales, as in worked metal, forging and castings. As I said, that if the scales are present on the workpiece surface, in that case this grabbing of the tool at a time material of the T1 maximum, in case the workpiece material particularly is harder, like if the scales are there, I already explained what are scales. All right. So, then of course, the tool wear will be more and even the tool may break. So, that is what it is telling, that not suitable for workpiece with hard abrasive scales, as in hot worked metals, forgings and castings. Okay. In that case, the tool wear will be excessive, and that is why it is not suggested that the down milling is performed immediately after the casting or immediately after the metal working process, because after the metal working process and the casting, the layer at the top will be normally harder than the layer lying inside, okay, or the hardness of the top layer will be more. Okay. These are the milling machines. These machines we will see in the laboratory. Okay. This is the horizontal milling machine, because the axis of the milling cutter is horizontal, okay. And here, since the axis of the milling cutter is vertical, so this is called the vertical milling machine. Okay. So, in the horizontal milling machine, you will see that on the base the entire machine is located, including the overarm, okay, on which we have the milling cutter. All right. Milling cutter is mounted on the arbor, and the entire arbor is rotating, and this is the support. All right. This supports the arbor, okay, and arbor, and one end of the arbor is with the spindle of the machine, and this end is attached to the support. All right. Now, here we have the saddle. This saddle moves in this direction, in the y direction, that is the cross direction, and this is the feed direction. This is the work table. Work table moves in this direction. So, we will have the x and the y, both in both directions the workpiece can be moved. Workpiece, of course, is mounted on the table. Okay. This is the column of the milling machine, which is a part of the base, of course. This is called also the knee, okay, because if you see that here it is located in the middle. So, this is a base actually. On this, the saddle and the table, work table, they move in the direction perpendicular to each other. As I said, once again I repeat that this work table moves along the x direction, whereas the saddle moves in the feed in the y direction. Okay, that means in perpendicular to x. Well, in comparison to this, components are almost the same in the vertical milling machine, except that the axis of the milling cutter is vertical. This is the cutter. All right. Here, of course, this cutter is horizontal, and here also we have the base, the column, all right, the head, okay, the cutter here, as I said, table, and this is given the feed. This is the x axis direction, and on the knee we have the saddle, which is given the y axis direction. So, other things are more or less the same thing. Next is the broaching operation, and the broaching operation is very typical operation. That means, it is somehow different than the other operations, in the sense that here the feed is not given to the tool separately, in the sense that for feeding, like that concept which we had so far, which we have seen in case of turning, in case of milling, okay, in case of drilling even. So, the feed is given by increasingly given the diameter of the teeth. Okay. Now, let me explain it to you. If you see this drawing, okay, this is given in the horizontal direction. That means, here the cutter moves a multiple tooth. These are the multiple tooth cutting tool linearly relative to work in the direction of the tool axis. So, if you can see that the depth here, of course, it is a two dimensional, that is why I am calling it as a depth. So, this depth is less than this depth is more, this is less than this depth is less than the next one, and this depth is the less. So, when the tool will be moving, okay, this is the broach, this is called the broach. When the tool will be moving, it will be removing this much material, and this tooth will be removing this much material. So, when it will go like this, it will be moving, it will be removing actually the total of this and this. So, final tooth will be removing, see, the material which will be sum of the depth of cut of all the other teeth ahead. That is what is the difference between the broaching and the other processes. So, as a result, what will happen, that the last tooth which will be actually cutting, and as you understand that tooth will be taking the finish cut, because that is the final cut. So, that tooth will actually give the finishing of the workpiece surface. Now, the all other teeth, they will have the rough cutting. Okay. So, this is the advantage of the broaching, that here you get the machining process done by one tooth, one tool. Okay. And here specifically the feed motion does not have to be provided, and broaching is done actually for making the slots, making the keyholes, okay, and for many other purposes where you need really the very high quality, and the surface roughness of the flat when it is made, or the groove when it is made, okay, internal slots, they are very high. In case of broaching, the surface finish is normally better than in other cases. Now, advantages are, as I said, that good surface finish, okay, close tolerances, meaning that if we have suppose the tolerance of the hole to be made very rigid, okay, plus minus let us say 0.01 or 0.02. So, this kind of a tolerance can be adhered to by means of broaching, that is what we are telling. Variety of work shapes possible, I already named those different shapes, I will show it to you also. Cutting tool called a broach, BROACH. Owing to complicated and often custom shaped geometry, tooling is expensive, and tooling is also expensive because here the entire broach, which is very heavy, which is very big, which can be very bulky, entire broach has to be made with the same material. And once again I will repeat that the tool material is very expensive, I told you this already. So, therefore, when instead of making the tips where the cutting process will be held, okay, or cutting process will take place, the entire broach tool has to be made with that same material. So, that becomes therefore very expensive. Now, that is why the broaching process becomes sometimes more expensive than other processes. These are the internal broaching shapes. Say this is the hole with the slots here, it may be used for the keys, so the keyholes. This hole is of a different types holes can be made here. Triangular shape of the internal hole, this is a slot, this is a T slot, this is another slot with a semicircular shape here, okay, and this is the square slot, square hole. So, if you see here that this is a cylindrical surface and this hole is the square hole, and as you understand that the making an internal square hole is very difficult otherwise, because drill will always make you a cylindrical internal hole. So, if you have to make a square cross section hole, internal hole, that too, here the broaching is one of the very few options. Okay. Performed on internal surface of a hole, a starting hole must be present in the part, because of course, you understand that otherwise the broach cannot be operated on a like drill. Drill is made on the cylindrical surface where no hole is made so far. Okay. But after a hole is made by drilling, like we do the reaming, the broaching process is performed. To insert the broach at beginning of stroke, otherwise will be difficult. Okay. Next topic that we will be discussing in this topic of the machining is the abrasive machining processes. Well, let me first give you a preamble that why these abrasive processes are used and why these processes are called the abrasive processes. Okay. Now, the tool material, as we keep telling, that these have to be harder than the workpiece material, and that percentage is quite high, that is from 35 to 58% we said. Okay. Now, and the metallurgist they are coming up with the newer and newer materials with the harder property, with the better properties, with much more hardness. Okay. But those materials have to be machined, has to be shaped, and therefore, the tool material that you will be using for machining those components, okay, hard components, they have to be harder than that component. So, there comes the problem. So, of course, there are hard particles like aluminum oxide, boron carbide, silicon carbide. Those hard particles can be used to machine those kind of hard materials, all right. But in the nature, those particles, hard particles, come in the form of grains only, like sand for example. This is aluminum oxide. Okay. Similarly, the silicon carbides are there. Okay. Similarly, the diamond is there. Diamond of course comes in the crystal level and so on. So, to make a tool out of that, like a cutting tool, they have to be combined together. They have to be glued. They have, all these grains have to be glued. So, that is how the cutting tool is obtained, like grinding wheel, you know that, or the lapping or the honing and so on. So, those hard particles, they abrade the softer material. That is why the process using the grains like aluminum oxide, boron carbide, silicon carbide, they are called the abrasive processes. Okay. Now, if you see here, hard particles like aluminum oxide, boron carbide, silicon carbide, etc., they abrade the softer materials. As I said, machining processes that use such particles are called the abrasive machining processes. Now, the material removal by action of hard abrasive particles usually in the form of a bonded wheel. So, as I said that those grains have to be given a shape of a tool. Okay. So, very popular is the bonded wheel, and that is called the grinding wheel, as you know that. So, in the grinding wheel, all those hard particles, abrasive grains, they are bound together, okay, with the help of some kind of glue or resins. We will come to that. Now, they are bonded overall. So, generally used as finishing operations after part geometry has been established. Conventional machining, by established conventional machining. So, here the sentence is to be read that finishing operation is done, okay, after it is machined by any conventional machining, all right. Now, grinding is most important abrasive processes. So, as I said that there are abrasive processes like grinding, lapping, honing. Okay. Out of that, the grinding, super finishing is also there. So, out of that the grinding is one of the most popular operations. Material removal process in which abrasive particles are contained in a bonded grinding wheel that operates at very high surface speeds. Okay. So, when we say that the grinding wheel the grinding process operates at a very high speed, that very high speed is normally really very high. This is like 10 to 80 meter per second. Okay. So, just imagine that this is meter per second and this is a very high speed, and therefore, if you see the grinding machines, bigger grinding machines particularly, you will see that the grinding wheel is always shielded, okay, by a shield which is called the apron. So, it is because if the grinding process during the grinding process when it is rotating, particularly when it is not balanced properly or a particular part of the grinding wheel breaks, in that case that broken piece can act as a bullet literally, because it is coming at a very high speed, and if that particle or that part of the grinding wheel hits a person, the operator for example, then it can be very fatal. Then other abrasive processes like honing, lapping, super finishing, polishing and buffing, these are the other processes which are also called the abrasive processes apart from the grinding process. Well, the grinding wheel consists of the abrasive particles and the bonding material, all right, because the materials have to be properly bound inside the grinding wheel. So, that binding material is important because the grinding wheel, how strong the grinding wheel will be, that depends of course on the binding material that I am coming to. Abrasive particles accomplish cutting, all right. Bonding material holds particles in place and establishes shape and structure of wheel. What is structure we will explain after a while. Now, grinding wheel parameters, like these are the 5 parameters: type of abrasive material, grain size, wheel grade, wheel structure and the bonding material. On these 5 parameters, the grinding wheel performance will depend, like how the grinding wheel is performing depending on the type of the abrasive particles. It depends on the size of the abrasive particles. It depends on the what kind of grade the abrasive wheel has, or what kind of a structure the abrasive wheel has, or how is the what is the strength of the binding material, or what is the bonding material that the that is used to get that to fabricate the grinding wheel. So, all these 5 factors including the bonding material, we will have the performance of the grinding wheel defined. Let us see one by one. Type of abrasive material. Now, in abrasive materials, commonly used abrasives in the machining, that means making the grinding wheel or the honing sticks or the lapping, during the lapping the paste that is made, I am coming to that. So, here basically we have the 3 which are used: aluminum oxide, which is designated by A, silicon carbide, which is designated by C, and the diamond. Rarely used are the cubic boron nitrides, CBN, because these are for, and the diamond also it is rare. So, basically these 2 are for very hard workpiece materials, very hard, when the workpiece material has to be brittle and hard. There are super abrasives. These are the super abrasives used for very hard materials like glass, and they are also very brittle, and it cannot be ground without the CBN or the diamond grinding wheel. So, most popular are the therefore aluminum oxide Al2O3, used for grinding steels, ferrous alloys, bronze and the other high strength material. Whenever there are high strength material to be ground, then the aluminum oxide has to be selected, that is the Al2O3. Silicon carbide is given as SiC, and that is designated as the C. And what is that designation I am coming to, that we will actually specify the performance of the grinding wheel. Silicon carbide used for grinding cast iron, brass, aluminum, hard alloys, and the carbides. So, you can see that silicon carbide normally they are more expensive than the aluminum oxide, and they are used for grinding the hard materials, therefore, like, and hard and brittle material. The hard material normally are also the brittle materials. Now, the cubic boron nitrates, diamond, I already told you that they are used for for grinding very hard materials, glass, carbides, ceramics, etc. Regarding the grain size, that means how we are defining the performance of the grinding wheel depending on the grain size is the following. Grain size is expressed in terms of the sieve number. Sieve number is Sn, suppose, which corresponds to the number of openings per linear inch. What does it mean is the following, that just imagine that if you have an opening which is 1 inch by 1 inch, let us say this is a square, this is 1 inch and this is 1 inch. So, how many openings are there, that is actually given by the sieve number. Let us say these many openings are here in this. So, this is 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. So, there are 25 openings and the sieve number Sn will be equal to 25 for this. Okay. So, this means that if you have this kind of a sieve and if you put the let us say sand on that sieve and then you try you vibrate it and you will see the particles which are coming, that will be up to a sieve number of 25, okay, and which will be remaining there, that will be more, it will be different from the 25. So, how different we are coming to that. So, whatever sieve number will be given, that signifies that the number of openings in 1 square inch sieve, okay, that is why it is called the sieve number. Now, the diameter of an abrasive grain dg, let us say we will designate it, this is given by 0.6 by this sieve number. Okay. So, this is inversely proportional to the sieve number. So, as you understand that more the sieve number, less will be the diameter, okay, and vice versa. But this is given in inch, mind it, because this formula is taken from the American source, and therefore, we have to convert in India, we have to convert it into millimeter or micron when we are defining the diameter of a grain, because the diameter of a grain, that means a sand, is very small, right, and this is a mean diameter, because it is not really a very round shape to say that this is a diameter actually. So, it can be of different shapes and we take the mean diameter. The diameter of the abrasive grain, therefore, finally, you will find out from 0.6 by Sn, and Sn will be given. Now, Sn, that number, this is given in different grades, like for example, 10 to 24, if the sieve number is 10 to 24, those grains are supposed to be the coarse grains, because the diameter will be bigger, okay, 24 will be here. So, it will be bigger diameter. Then the other like 30 to 60, 30 to 60 sieve number will be called as the medium type of grain. They are not very coarse, but they are little finer. 70 to 180, these are the finer grains, and 220 to 600, they are very fine grains. Okay. So, these size or this is a international standard, and everywhere in the world we use this kind of a standard to define the diameter of an abrasive grain. Okay. Now, next is the grade. The grade indicates the strength of the binding material. Now, when the workpiece material is hard, the grains wear out very easily and the sharpness of the cutting edges is quickly lost. This is known as the wheel glazing. Okay. I will explain it to you why it is important. Let us say first of all, the phenomena is that when the workpiece material is hard and the grinding wheel is hard, then the grinding wheel of course will be worn out, because the surface is very hard, workpiece material is hard. But now, since the grinding wheel is hard, that means the binding material is very hard and it is holding the grain very tightly, then that grains will not be dislodged easily, and on the surface of the grinding wheel these worn out grains will stay. Okay. And that is called the glazing, because in that case the entire wheel surface will be glazed, will look like it is illuminating the light. So, it is a glazed wheel, and the glazed wheel will not cut efficiently, because it will cut less and it will rub more, it will consume more power and the more force. So, therefore, it is not effective, and we want those worn out grains to come out of the wheel surface, because behind those worn out grains we will always have the sharp grains. Okay. So, the sharp grains will remove the material more and it will consume less power, it will consume less cutting force as well. So, it is always beneficial that on the wheel surface we have the sharp grains, and if the sharp grains are worn out, we have to take them out. I mean, it is desirable that those worn out grains come out of the surface, because otherwise we will not get the sharp grains which are located behind those worn out grains. Okay. To avoid this problem, a soft wheel should be used, because if the workpiece is hard and the grinding wheel is soft, then after getting worn out, those grains will be dislodged quickly, and then the sharp grains will be coming out behind which were behind the worn out grains. So, the international standard is that A to H, these are the soft wheels, okay, and the wheels designated from J to P, okay, these are the medium wheels, and those wheels designated as Q to Z, these are the hard wheels. Okay. So, here all the 26 letters of English alphabet except the O and the I, because the O looks like 0 and I looks like 1. So, except O and I, all the other 24 alphabets are used to designate the grade of the grinding wheel. So, once again A to H is the soft wheel, okay, and similarly J to P and Q to Z. Q to Z is the hardest. Next to grade is the structure. Okay. Now, here in a very enlarged way, the surface of a grinding wheel is shown, and you can see that in between the grains, okay, there is a void. Void is the space to accommodate the chips, like in case of the milling cutter. In milling cutter, I have just now shown it to you when we are discussing the up milling, down milling, that between the teeth there is a space that is called the void, and VOID, and that in those voids the chip is accommodated. All right. Now, if the void is small, there the small chips of the grinding wheel will be entering and won't be able to come out. Okay. In that case, the entire wheel surface will be clogged by the small chips in these voids of the grinding wheel, and that is also a bad, like in case of the here wheel glazing. In that case, since the sharp grains will not be able to be in contact with the workpiece, and these chips which are clogged in the, or which are trapped inside these voids, they will actually rub and consume more power. Okay. So, this is what actually here it is written. If the voids are too small for the chips stay in the wheels blocking the voids, and this is known as the loading of the wheel. So, wheel loading is also not desirable like the wheel glazing. So, those layers, that means the, in this case wheel loading case, it is the layer of the clogged chips, and in case of wheel glazing it is the layer of the worn out grains. Both of these have to be removed, that means that layer has to be removed, and that is done by the following way. Suppose we have the grinding wheel like this, and the glazed wheel or glazed layer or the loaded layer will be on the top, right. This is the grinding wheel axis, let us say, and this is rotating. So, this is the wheel, let us say. These are the grains. So, now here this is the diamond pin, okay. This is a diamond pin, and that diamond pin is used to remove the surface layer from the grinding wheel. Here it is given the feed like this, it reciprocates. Okay. So, this process, as many of you will be knowing, this is called the wheel dressing. Wheel dressing is done to remove the layer from the wheel surface where either the worn out grains are there or the clogged chips are there. Okay. So, after it is removed, this thin layer is removed. After that, you will find that the wheel will be with the sharp grains on the surface. Okay. So, that will cut more, that will consume less power and so on. According to the international standard, there are 17 grades of this structure, the grinding wheels. These are from 0 to 16. Now, 0, 1, 2, 3 etcetera, these are the dense wheels, okay, or the closed structure. Closed structure means the voids between them is very small, okay, and starting from probably 10, 12 and so on, and after that these are the open structures relatively, let us say, in comparison to 0, the 16 is the most open structure. That means, if the structure is designated by 16, that means the voids are very big, okay, and probably there will be no possibility of the chips getting clogged there if when the chips are small in case of the grinding. All right. Now, the recommendations are that for hard work material, we need the closed structure. We should select the closed structure, okay, or grades like 0, 1, 2, 3, 4, 5 like that. Open structure means voids are relatively large and grains are relatively small, okay. Recommended when clearance for chips must be provided. So, obviously, I already explained it to you that these are the wheels with the open structure, okay, where the voids are relatively large. That should be recommended when the clearance for the chip is to be provided. Now, the dense structure means the voids are relatively small, okay, opposite to this open structure, and grains are therefore larger, and that is recommended to obtain better surface finish and the dimensional control. Okay. This is a dense structure. All right. Now, next to that is the and finally is the bonding material. In the bonding material, there are various bonding materials, particularly these 6 bonding materials I have noted down. These bonding materials are vitrified bond, okay, resinoid, silicate, shellac, rubber bonds and the metallic bond. So, these are the most important bonds which are used, binding material which is used in case of the grinding wheel. Now, the vitrified bond, it is designated as a letter V, capital letter V. These are very strong, rigid, they are commonly used, okay, they are available abundantly in the nature and they are not very expensive. All right. So, next to the next bonding material is the resinoid, and the resinoid is designated by B. Resinoid provides the shock absorption and the elasticity. They are strong enough. All right. They are probably as strong as the vitrified bond, but they actually can provide a little bit of shock absorption. This is important, you know, when particularly there is an interrupted cutting, for example. In case of interrupted cutting, each time the tool is entering the workpiece and exiting from the workpiece, there will be a shock, okay, shocking load. So, impact loading. So, that load has to be withstood by the grinding wheel, and the grinding wheel may be brittle. Okay. So, therefore, the resinoid is used as a bonding material to overcome that kind of a shock load or the impact loading. Okay. So, the resinoid overall provides the shock absorption, to some extent the elasticity, not very high elasticity, but to some extent, and they are strong. Now, the silicate, this is a very important bonding material and very widely used in case of the grinding wheel, particularly when we need to have the softness. Okay. Softness means the grinding wheel grains, they will dislodge quickly. So, in that case you understand that when the grinding wheel grains will dislodge quickly, that means the sharp grains will always be there, and once the sharp grains are there on the surface, I already told you that the power consumption and the force will be less. So, therefore, the temperature occurring will be less. So, therefore, this kind of bonding materials like silicate, they are used for the cool operation, so to say. Okay. And the cool operation means that those operations where we do not want the high cutting temperature or the high heat generated. Okay. For example, when we have the turning tool, okay, with the cutting insert, all right. I have already shown it to you that there are inserts which are used in the milling cutter, there are inserts which are used in the turning tool, and inserts which are used also in the drilling or the drill. Okay. Now, when those inserts are very small, when they have to be reground, okay, we do not want the temperature to be raised in the vicinity or in the vicinity of that edge, because otherwise the vicinity of that edge may be thermally deformed. Okay. In that case, the silicate is very popularly used because it always allows the dislodging of the grains quickly, and always the sharp grains will be available on the surface. So, therefore, so to say, there is a cool operation, and that cool operation can be performed by the silicate bonding material, where the heat generation will be less, relatively less. Next bonding material is shellac, and shellac is designated by E, that is used for making thin but strong wheels possessing some elasticity. You have seen the elasticity is provided by the resinoid as well. To some extent, the shellac also can provide the elasticity, but basically this is made for the thin, okay, but strong wheels. So, those thin and the strong wheels, they are actually made for parting off the material. Like for example, there may be some cylindrical job which are very diameter is very large, okay, and that has to be cut off, parting off, okay, operation. So, when it has to be cut off, we want the surface, this face to be of very high quality. That means that that surface has to be exactly perpendicular to the axis of the cylindrical job. In that case, of course, these kind of wheels, thin wheels, but they have to be strong, because as you understand that since the diameter is more, as it is going inside towards the center, it can actually vibrate, and the wheel, if it is not very strong, it will not withstand, and it has to be also it has to possess some elasticity, because to withstand that vibration in case it happens in the workpiece. Next to that, there is another bonding material which popularly used for making the flexible wheels. These are the rubber bonds, okay, and the rubber bonds are designated by capital R, okay. And finally, we have the metallic bond. Metallic bonds are designated by M, and the metallic bonds are exclusively used for the diamond wheels. When the grains are diamond grains, they are bound by the binding material of the of some kind of metal. Okay. Now, if you see, starting from the very beginning, we have the abrasive material. First, they are designated by a letter of the alphabet. Next is the grain size, they are designated by a number. Next is the grade, again by a letter, structure by a number, and finally, the bonding material as by the alphabet again, the letter again. So, these are the in sequence. First, it is by a letter of the alphabet, then a number, then a letter, and so on. So, the performance of the abrasive of the grinding wheel, it is given by this number. Okay. So, when we are purchasing the grinding wheel, we have to mention this sequence of the parameters. For example, we can say that this is A46, H6 and the V. Okay. That means, the abrasive material that is used here is the aluminum oxide. Okay. The size of the abrasive grain is 46, and the diameter of the grain, we can find out that this is, if you see that where from I am taking, it is from here, that 0.6 by Sn. Okay. So, we can find out that this diameter will be 0.6 divided by 46, it is in inch, okay. That you can convert to micron. Next is the grade. So, in the grade I will show it to you that this grade is here, this is the soft wheel A to H. Okay. Then 6 is the structure, and I will show you that structure. We have said that 0 in the beginning, it is the dense structure, that is a closed structure. So, this will be the closed structure, relatively closed structure, and V is the vitrified bond. This is the vitrified bond which is strong and rigid and commonly used. So, if you tell that you need this kind of a grinding wheel, or if you have a grinding wheel with this performance, you will be knowing that this grinding wheel to be used where. For example, this grinding wheel cannot be used for grinding cast iron, for example. Okay. Why? Because we have this limitation that aluminum oxide used for grinding wheels, grinding steel material, ferrous alloys, bronze, and for cast iron, which is the brittle material and hard material, for that you need to have the silicon carbide. Okay. So, that is one thing. Second thing, for example, here it is the size. So, you cannot use that for very finishing operation, because this is the coarse grain, okay, not very fine grain, because it is inversely proportional to this number. All right. Since it is not very fine grain, so this grinding wheel is not for the finish operation, and so on. So, you can find out that if you have to, other way saying that suppose you need to have a particular surface roughness, okay, a particular material that is being ground, okay, a particular condition that is given to you of the workpiece material and the parameters. In that case, you have to judiciously select that what should be the grinding wheel, okay, and you have to tell only in this way. Of course, there could be a manufacturer's code here and at the end. All right. So, the manufacturer of the grinding wheel may have their own code here in the beginning and at the end, but here these are the 5 parameters by which the performance of a grinding wheel will be defined. Okay. So, here it is written that standard grinding wheel marking system used to designate the abrasive type, grit size, abrasive type, grit size, grade, structure and bond material by this. Okay. Also provides for additional identification for use by the grinding wheel manufacturers in the beginning and or at the end. Okay. So, this is the complete signature of a grinding wheel. Like you must remember what we have discussed, the tool nomenclature. Let us say turning tool nomenclature. There we had the 6 angles and the tool nose radius. Okay. By 7 parameters we were defining the type of the tool that we are actually designating or we are using. Similarly, in case of abrasive wheel also, we designate the abrasive wheel performance by this. And while purchasing the grinding wheel, you have to also mention this kind of 5 parameters. So, once again these 5 parameters are the abrasive materials, okay. These are the aluminum oxide, silicon carbide and so on, okay. Grain size, grade, structure, okay, 0 to 16 and the bonding material. The rest of the material I will discuss in our next discussion session. Thank you for your attention.